artificial spin chains on superconductors in order to study topological superconductivity. So first of all, I would like to mention the people who did all the work. So this was mainly PhD students Lukas Schneider and Philipp Beck. And we are working in the group of Roland Wiesenlanger, who also will give a plenary talk on Monday morning. So we have very good theoretical support by Levente Rocha and also the group of Laszlo Szyniok, and also here by the group of Doroposke in Hamburg, and also Stefan Rachel's group. Okay, so what I will talk about, I will first motivate is what we would like to study is one-dimensional topological superconductivity in Majorana bound states, and maybe you know this very famous model, the Kitsaev chain, which is essentially a spinless one-dimensional superconductor. And if you calculate the band structure of this such a system as a function of hopping and chemical potential, you will see that you have two separate phases. One is a trivial phase, and the other one is a so-called topological phase. What you also see here is the intensity in this bands of the U part of the Lyubov quasi-particles, which I will tell you in this talk you can essentially also see in the experiment. And thereby you have a way of distinguishing between such a trivial gap or a topological gap, because in the topological case you have some kind of essentially some avoided crossing here, and you then would be maybe able to decide whether you are in trivial or topological phase. So this is something which hasn't been done so far. Because usually you need very clean systems to do so. Mostly what people have done. Sorry, is there a question? Mostly what people have done is to look at the local electron density of states, which is shown here as a function of the two of the parameters. And as you can see, when you enter the topological phase where this gap reopens, that you also localize these famous Majorana bound states at the edges of your wire, right? And this is something which mostly the people have tried to look for in these systems, and the best would of course be if you could combine both, that you see topological gap and the Majorana bound state at the same time. So what you also would have to keep in mind is that we are working here with confined systems. So that means that these Majorana bound states, because they have a certain size that's such that they can also interact with each other, and thereby if you have very short nanowires, these Majorana bound states shift off from the Fermi energy, and then as a function of wire length you have some kind of oscillation, and this is something which we think we have seen in short wires, as I will tell you. So the question is, of course, how to build such a spinless superconductor, because usually superconductors have, of course, a spin, and so there have been these proposals that you can try to work with triplet superconductivity, but these systems in the nature usually are not so often there, so you can try to design them, and the kind of recipe that you can do is that you proximity couple a chain to an S-wave superconductor, and then you induce Zeeman energy with a magnetic field or with ferromagnetism, and thereby essentially only get one spin sort, which is then essentially a spinless system. And then, in order to couple these spins together, you need spin-orbit coupling such that the S-wave superconductor can couple these spins together. And in case, instead of 2 and 3, you can also use spin spirals in order to solve this. So we are working with spin chains on superconducting surfaces, and here I have to tell you a little bit about what atoms do on a superconductor. They induce, if you have a spin 1/2 system, they induce these so-called Yusheva-Rusinov states, which are in the gap of the superconductor with energies symmetrically around the Fermi energy, and the energy of these states is shifting as a function of the Kondo coupling of the local spin to the conduction electrons in the superconductor. You can have some asymmetry here in the intensity. This is also important for the experiment. And now what happens if you couple these Yeshiva-Usmanov states together in a chain? Then it has been shown that you can form these Shiva bands here. And this is shown here as a function of the exchange coupling to the superconductor. So the stronger you do the exchange coupling, these Shiva bands will broaden and also then at some point cross the fermion. So if you are in this regime here for small quantum coupling or very large quantum coupling, then you essentially only get Shiva bands which are all over the chain with a trivial gap. But when you are in the right regime where the Shiva states just cross the Fermi energy, then you can get into this topological superconducting regime with Majorana bound states on the ends and peak at the Fermi energy, localized in the ends of the chain. And this is nice because it's essentially working for very large ranges of angles between neighboring spins or spin-orbit coupling also in ferromagnetic chains. But as you see, you need to tune these Shiva bands close to the Fermi energy via the quantum exchange coupling. So this requires a lot of material work and detailed work. So here I show you just some famous previous experimental work on the spin chain platform. So you might know this work of the group of Yazdani and also Katharina Franke and others, where they have indeed seen indications for Majorana fermions at the ends of these chains, but these systems are quite disordered, and you cannot really follow the evolution from the Shiva states to the Shiva bands. So there has been a lot of work in the group of Franke, Liljeroth, and others on the single impurity Shiva states. So if you have a 3D impurity on a superconductor, you get more than one Shiva state because you have these 5 d orbitals, and for each orbital you can have Shiva states which then have symmetries which resemble those of the orbitals. And then in our group we started to build the chains atom by atom using the tip of the scanning tunneling microscope, as you can see here for iron cobalt chains on rhenium, where you also see already indications for Majorana fermions on the ends of these chains. But then what we really want to do is that we put together these two things and really start from the single impurity Shiva states and build bands from that. And this I will show you here in my talk, and this also has been already started in the group of Katharina Franke. All right. So how do we prepare our samples? We do all that in ultra-high vacuum and investigate the samples in the same machine in this experimental setup, which has base temperature of 0.3 Kelvin and maximum field of 12 Tesla perpendicular to the surface. So in this talk, I will present the results on niobium, on transition metal atoms, in this case manganese on niobium. The niobium 110 surface looks like that. It has a twofold symmetry, and this is very nice because then you have several directions where the atoms will have different distances. How do we prepare manganese atoms on niobium? We first prepare a very clean niobium substrate by high temperature flashes, and then dose manganese onto the cold surface, which will then, we then have a statistical distribution of manganese atoms. And then we can first study the Shiva states of the single manganese atom. So let's look at one of those atoms. If we take spectra on the substrate, we can see nicely the very large gap of the niobium substrate, which has a size of 2 delta equals 1.5 millielectron volt. Now, if we take a spectrum with a scanning tunneling microscope on top of such an atom, you will see that there are additional states inside the original gap. And in this case, we can we can see 4 different states, which we name alpha, beta, gamma, delta. So this alpha state and the delta state are the most intense ones. And you also see here this asymmetry in the intensity of the alpha state, which is much more intense below the Fermi energy, while the delta states the particle and whole part are more or less have the same intensity. Now you can sit on each of those states and resolve the spatial shape of the state around such an atom. And you see that they have very distinct shapes. The alpha state is more or less circular symmetric, while these beta, gamma, and delta state have certain lobes. So this already reminds you of these symmetries of the d orbitals of the manganese atom, and therefore we can conclude that for each of those occupied orbitals we get a Shiva state. So now we want to work with these Shiva states and hybridize them in chains, and for that we use atom manipulation. So we basically take an image and look where the atoms are, and then we drag them with the tip across the surface in order to build very well-defined and very clean, defect-free chains of manganese atoms on the surface. And you can count the atoms, so you know exactly how many atoms are in these chains. And as I said, you can align these chains basically along many different directions. So this is an example for chains along the 001 direction on the surface. So we can build, as I said, chains with different numbers of manganese atoms. In this study we did up to 36 manganese atoms, and I have no time to go into detail with that, but we can also now take this magnetic tip, this is described within this publication, and measure the magnetic state of these chains, and by taking spin-resolved scanning tunneling spectroscopy data in different magnetic fields. And as you can see here in this data, at minus and plus half a Tesla, you do not see any contrast along the chain, so we are pretty sure also in comparison to first principles calculations that these chains are in a ferromagnetic state. Okay? So now you have to remember that we have two very intense Shiva states on these chains, on these ferromagnetic chains. So the alpha state is more or less localized on top of these atoms, so it will lead to a band which is also located more, if they hybridize, it will lead to a band which is localized on top of the chain, while we also have this delta state, which is now sitting on the side of the chain, so we expect that we will have an additional band if they do not strongly hybridize on the side of the chain. Okay? So now let's look at the evolution of the states as a function of chain length. So this is the number of atoms in the chain, and here I show you the spectra in a color plot, which is a spectrum which is averaged over chains of increasing n, and again you see here the alpha state here and there and the delta state. Now if you increase the length of these chains, you see that from the alpha state you get some first splitting and then evolution into some kind of band, which has a bottom at about plus 0.5 Tesla here, and you see that it also crosses the Fermi energy, and inside the band you see some discrete levels, which, as I will tell you in a minute, is due to confined states within this alpha band. And you also already see that there is a kind of gap in this band at the Fermi, right? So we can see whether this is really due to confined states by doing some kind of fitting. If you have a particle in a one-dimensional box, then you expect that these states go with 1 over n squared, and this is exactly what we see, for example, for this n equals 0, n equal for the first state. But we can also prove that these are really confined states by now taking spectra along on top of such a chain from the left side on the substrate to the right side from the center. And this is shown here as a function of the position. You see here on the substrate we have the coherence peaks left and right. And inside the chain you can clearly see these confined states with 1, 2, 3, 4, and so on maxima. And also again this small gap here. And now if you increase the length of the chains, you can nicely see how these states evolve, how the energies shift because of the confinement conditions. And you can now of course also fit sine square wave to this data and extract some kind of dispersion of the scattering vectors, and this is shown here with a procedure which is described there. Right, so you see some kind of very nice band, which has a very intense part here in one component of the Wiebe of quasi-particles, and you clearly see here this crossing of some gap, and you also can see the particle hole partner in a very much lesser intensity here. So we are pretty confident that we have a gap in this alpha band. Okay, so then the question is, of course, where this gap comes from, and we did some modeling here with type binding models, single band type binding model with an effective Rush-Spin orbit coupling, and with parameters consistent with the energies and particle hole asymmetries of the single atom alpha state, and you can see that we can nicely fit these bands, and these calculations show us that at least this alpha band has a non-trivial topological index, right? As you can see here by comparison, if you go to the trivial parameter regime. And as these Shiba states are non-spin degenerate, as they originate from non-spin degenerate Shiba states, we think that most probably this gap comes from a pairing mechanism with a p-wave contribution. Then, of course, the question is, where is my run? Because as I told you, if I'm in this topological regime, then I expect that in this band I would have a state which is then localized, an edge state which is localized on the ends of the chain, but we do not see this in our data. So you can now think about whether the chains are maybe too short, but if we take this dispersion and calculate the localization length of the Majorana's, you get something like 4 nanometer, which is less than our longest, much less than our longest chains. So the point that we have to consider is here that we have to recall that we have, of course, additional Shiba-Rosen states. Right? We do not only have this alpha state, which does this band, but we also have these delta states, which will probably be located on the sides of the chain. And these you can see if you now take maps. Not only, if you do not only measure the local electron density of states on top of the chain, but also on the side on such a two-dimensional map. And here you see in these maps again the circumference of the chain, and you see inside the chain nicely these confined alpha states with 1, 2, 3, 4, 5, 6, 7 maxima, 6, and so on. But you also see exactly at the distance where the delta state would be positioned, you see additional confined states here. For example, here with 3 maxima, 2, and 1. And if you look very carefully in our analysis, these states are also visible in this expected band structure, and they are inside the gap of the alpha. Right? So this gap is somehow closed by these delta states. And this could be a reason why in these chains we do not resolve the Majorana state of the alpha band, because they could also hybridize with the Majorana states of other bands. And then the system will get trivial. However, it may also be that the delta band 5 minutes has a topological gap as well, which is too small to be experimentally resolved. And this is also suggested by a recent publication of the group of Stefan Rachel, who showed that in this system we will get Majorana states which are looking more or less like the ones we have seen here in the delta. So then the question is, can we somehow get rid of these overlapping states? And we can indeed by now building chains along a different direction. So far I have told you our study of chains along this direction. And now we can also study chains along this direction, where the distance between the atoms is larger, and then probably the hybridization of the alpha state gets smaller, such that the band which gets narrower, and maybe then they will no longer cross the fermion. So how does the band structure of these chains look like? This is shown here. So indeed, in these chains, we get an alpha band which is not crossing the Fermi energy. It's off the Fermi energy, but there is still the additional delta band which is still crossing the Fermi energy. So we essentially, in this case, have only one intense band. And we also know from single band type binding model calculations based on ab initio adjusted to the pairs that this delta band will indeed have a topological gap of the size of about 100 microelectron volts, which is just at the border of what we can resolve. Okay, so that means that we would expect indeed at least Majorana modes in this band, and if we now take again data first in this large energy region, we just see these alpha states which are on top of the chain, but if we go to zero energy now, we see states which are indeed localized on the edges of the chain, right? And you can now study these states as a function again of chain length. Here again, I show you the data, the local spectroscopy along the chain. You nicely see this zero edge mode, which is localized on the edge of the chain. And now the interesting thing is, if we just add one additional atom to this chain, you see that this state shifts away from the Fermi energy. And if I add an additional atom, the state comes back to the Fermi energy. So there seems to be a length-dependent oscillation of this edge mode, which you can also very nicely study if you do another measurement mode by just taking spectra only on the end of the chain as a function of length, and this is shown here, from 1 to 44 number of atoms. You see this nice oscillation of the edge mode of the delta band, and you can, if you separate this into even and odd length chains, you can see that there seems to be some even-odd effect, and in each of these even or odd chains you have some well-defined oscillation of these end modes. So we are pretty confident that we can assign this to so-called precursors of Majorana bound states, because if we take now the band structure, which we know from also the measurements and the calculations, and calculate these end modes using these realistic parameters, we see exactly the same oscillation as a function of distance, and apparently this even odd effect is just an accident, because the k vector is just at pi over 2d. Sorry, this means that I should stop, and I will come to a conclusion. So what we cannot resolve here in the data is there is a small topological gap which is just beyond our resolution. And why do we call those states precursors of Majorana bound states? The reason is that we can show by the model that there is still a very strong overlap between the modes from the left and the right edge, but you cannot really separate them into left and right Majorana modes. And what is also nice in the model is that we can estimate how long we would have to make the chains in order to really get unpaired Majorana bound states protected by a topological gap. And this will happen for chains which are about like 70 atoms long, which is 35 nanometers. And with this, I want to conclude and just put my conclusion on the screen. And I'm happy to answer questions. Thank you.
In typical situation, Majorana bound state should forming a flat band at zero energy. In your case, you have some crossing in topological gap. So you can explain this?
So that means that we can conclude that these states are not the Majorana from the alpha band. So this is a different orbital band, right? So it's a more complicated system. So apparently this alpha band, we do not see the Majorana mode. But we think that we see the Majorana mode from this delta band, which is crossing the gap of the alpha band. So this is let's say, then a two-orbital system. And then the Majorana mode would be exactly there, but the gap we cannot resolve for this delta band, because the chain the spin-orbit coupling here for this band is not large enough, and the chain then is still so short that the states are shifting, are oscillating still as a function of length. So they shift out of the topological, the very tiny topological gap.
Okay, thank you very much.